Hello, my good friends. My name is Kepsi Richard, and welcome to my online class. Today, our discussion on discrete mathematics will be on a very important property of relation, which is closure of relation. Before the video ends today, we will look at what a reflexive closure means, how to find a reflexive closure of a relation. We look at symmetric closure, how to find the symmetric closure of a relation. Then transitive closure, then how to find a transitive closure of a relation. This will be a very interesting engagement, so please be my guest. So we start things off with a reflexive closure. So we say a reflexive closure of a relation are maybe defined on a set is written as reflexive into bracket R. So when you see this reflexive into bracket R, it means reflexive closure of R, the relation R. And it is giving us the relation R union delta. Please check out my videos on how to combine relations, that's intersection and union of relations on YouTube. It will help you. So where delta are the self-loop relation of the set defined on the set where the relation is defined on. So now how do we find the relation of the relative closure of a particular relation defined on the set? So we say the relation R is defined on a set S equal to 1, 2, 3, 4 as R equal to the ordered pair 1, 3, 2, 2, 3, 4, 3, 1, 4, 3. We should find the reflexive closure of R. Or when you say reflexive R, is the same thing. Remember we said the reflexive closure of R will be equal to R, that's the relation R union delta. One thing you must know that when I say reflexive closure, that means the reflexive closure of a relation, that means the relation is closed absolutely, or the relation is reflexive absolutely. So we need all those possible values that will make the relation reflexive. We include them, and that's all. So where our delta, remember we said is the self-loop relations. So delta will be equal to, remember the set is 1, 2, 3, 4. So self-loop relation will be 1, 1, 2, 2, 3, 3, then 4, 4. Then we find R union the delta. So we'll put them together. So our reflexive R, the reflexive closure will be equal to, so now the self-loop relations union the relation R. So we'll put them together. So we have 1, 1, then we have 1, 3, that's this. We'll have 2, 2, we'll have 3, 3, 3, 4, or maybe 3, 1 first, then 3, 4. We have 4, 4, then 4, 3. So let's check and see if all the ordered pairs in R and all the ordered pairs in delta are in the relation. So we have 1, 1, 1, 1 is there, 2, 2, 2, 2 is there, 3, 3, 3, 3 is there, 4, 4, 4, 4 is there. Now we check this. 1, 3, 1, 3 is there, 2, 2, 2, 2 is there, 3, 4, 3, 4 is there, 3, 1, 3, 1 is there, 4, 3, 4, 3 is there. Then we say this relation is the reflexive closure of R. I hope you understand that. The next one is the symmetric closure. So when we talk of symmetric closure to a layman, the symmetric closure of a relation refers to all the possible ordered pairs that must be added to a relation plus the relation itself that will make the relation absolutely symmetric. Please check out my videos on the symmetric property of a relation, the reflexive, and all other properties of a relation on YouTube. So we said that the symmetric closure of a relation R defined on a set is written as the symmetric into bracket R. So if you see symmetric into bracket R, it means symmetric closure. And it is equal to the relation R union R exponent negative 1 and R exponent negative 1 is the inverse of R. Please Check out my videos on how to find the inverse of relation on YouTube. So, how do we do this? For example, we say given that R is equal to the ordered pair 1, 3, 2, 2, 3, 4, 3, 1, and 4, 3. Is a relation defined on a set A equal to 1, 2, 3, 4. We should find the symmetric R. So, remember the relation itself, R, is equal to 1, 3, 2, 2, 3, 4, 3, 1, and 4, 3. Then we can say the inverse of R will be equal to 3, 1. That means we flip 2, 2, 4, 3, 1, 3, and 3, 4. Then we can say our symmetric R, or the symmetric closure, is equal to R union R inverse. So that will be equal to, so we'll put them together. So what do we have? We have 1, 3. Then we have 2, 2. We have 3, 3. We have 3, 1. We have 3, 4. We have 4, 4. Then we have 4, 3. Let's check whether everything is there. So first we check for the R. 1, 3, 1, 3 is there. 2, 2, 2, 2 is there. 3, 4. 3, 4 is there. 3, 1. 3, 1 is there. 4, 3, 4, 3 is there. We check for the inverse too. 3, 1. 3, 1 is there. 2, 2, 2, 2 is there. 4, 3. 4, 3 is there. 1, 3. 1, 3 is there. 3, 4. 3, 4 is there. Then we can say this is the relation, is the symmetric R of the relation defined on a set A. The next one is a transitive closure. So we look at the last property, which is transitive closure property. We say transitive closure of a relation R defined on a set, also written as transitive into bracket R, is R exponent n. When R exponent n is equal to R exponent n minus 1, or R exponent n is a proper subset of R exponent n minus 1. Remember, when one set is a proper subset of the other, it means all the members of that set are equal to all the members of the other set. So very, very important. So what does this mean to a layman? So this means that you find R exponent 1. And remember, R exponent 1 is the same as R. So R exponent 1, since it's the same as R, we don't have problem. Now we find R exponent 2. Remember R exponent 2. Check out my videos on composite relation on YouTube. R exponent 2 will be equal to R composite R. If you are done, find out whether R exponent 2 is equal to R exponent 1, which is the same as the R. If it is equal, then R exponent 2 is the transitive closure of R. If it is not equal, you go further to find R exponent 3. And remember, R exponent 3 will be equal to R squared composite R. If R exponent 3 is equal to R exponent 1 and R exponent 2, then R exponent 3 is a transitive closure of the relation R. If it is not equal, then you proceed to find R exponent 4. And R exponent 4, remember, will be R exponent 3 composite R. So after that, you check whether R exponent 4 is equal to R exponent 3. If it is equal, then R exponent 4 is the transitive closure of R. If it is not equal, you go further like that until you get a relation that is equal. So now we take some sample problem and see how we can find that. So a relation R is defined on a set B equal to the members A, B, C as R equal to the ordered pair A, A, B, B, C, C, C. We should find transitive R. So how do we do that? So remember our R is equal to AA, AB, BC, and CC. Now we need to find R squared. And R squared, remember, is equal to R composite R. How do we find R composite R? We pair each of these other pair against each other. Please check out my videos on power relations on YouTube. Then, if the first element of one ordered pair relates to the second element of the second ordered pair, then the first element in the second ordered pair will relate the second element in the first ordered pair. So how do we do that? We take 1, 1, AA against AA. So you see that A will relate this A. Then we have the ordered pair AA. So we have the ordered pair AA. Now A against AB now. AA against AB. So you can see that it doesn't relate. Then we will not have such relations. We have AA against BC. You see that they did not relate. We will not have such a relation. Then AA against CC. They don't relate. We don't have such relation. Now we take AB. AB against AA. You see that the A relate this A. Then have the other pair AB. AB. Now AB against itself. It doesn't relate. AB against BC. It doesn't relate. AB against CC. We don't have such a relation. Now we take BC. BC against AA. No such relation. BC against AB. So you see that this relate this. We have the relation AC. So we have AC. Now we take BC against BC itself. It doesn't. We have BC against CC. It doesn't. Now we take CC. CC will not relate this. It won't. So we have CC against BC. You see that the C relates it. We have the other pair BC. So BC. Then CC against itself. CC against CC. You see that this C relates this C. We have the other pair CC as well. C, C. So we proceed to check whether R squared is equal to R. So we check. So we have A here, AB here, AB here. BC is here, BC is here. CC is here, CC is here. Well, we have AC here, AC is not here. So they are not equal. Or R squared is not a proper subset of R. Then we go further. So we conclude that our R squared is not equal to R. Or R squared is not a proper subset of R. Now we'll go further to find our R cube. Our R cube will be equal to R squared composite R. What does that mean? We take each of the other pairs in R squared and compare it with R. If the first relate the second here, then the first here will relate the second here. I hope you get that. So that's how we are going to do it again. So we take AA against AA. AA here in R squared against AA in R. So you can see that this R relate this R. We have the other pair AA. So AA. The next one, AA against AB. AA against AB. We don't have such relation. AA against BC. We don't have such relation. AA against CC. We don't have such relation. So we are done with AA. We take AB. AB against AA. You can see that this A relate that A. We have the other pair AB. AB. AB again against itself. That's AB against AB here. So we don't have such relation. AB against BC. We don't have such relation. Then AB against CC. We don't have such relations. We are done with AB. We take AC. AC against AA. You see that the A relate A. Then we have the other pair AC. We have AC. Then AC against AB, we don't have such. AC against BC, we don't have such. AC against CC, we don't have such. Then we are done with AC. We pick BC. BC again against AA, we don't have such. BC again against AB. So you can see that the B relate B. Then we have the other pair AC. But we have AC there already. Then we are cool. Then AC again against AC again against BC. So the first one is AC against AB. AC against BC. We don't have AC against. Okay, we are on AB. We are not up to AC yet. So AB against AA. We have this relation and A relate B. So AC against BC. AC against BC. We don't have. AC against CC. We don't have. So we are down with AC. We take BC. BC against AA. We don't have. BC against AB. So B relate B where we have the AC. So we're rather on the BC. Now BC against BC itself. BC against BC, we don't have such. BC against CC, we don't have such. Now BC, CC, that was the last one. CC against AA, we will not have. CC against AB, we will not have. CC against BC. This will relate it. Then we have the other pair BC, so B, C. Then CC against CC. We have such a list. Then we have the other pair C, C. Now we'll compare our R square against R2. So there is AA there. We have AB. We have AC, BC, CC. Then we can say that our R3 is equal to R squared, or R3 is a proper subset of R squared. Hence, the transitive closure or transitive R will be equal to the other pair AA, AB, AC, BC, then CC. I hope you get that. This is very, very simple if you get a concept. So today we have been looking at reflexive, symmetric, and transitive closures. We'll end it here today. Remember to subscribe to my YouTube channel. Until we meet again, my name is Kepsi.